blood in my face. I love on my face. Just I'm done playing. Pouring the rain, yeah. It's blood in my face. I love on my face.
Good afternoon. Hello. Let's get started. So I'm happy that you obviously are half of the Netherlands who's not lying in bed being sick with a cold or a flu. So ready to dive into the thin film technologies tonight or this afternoon. And my name is Marina. I'm from the High Tech Campus team, and we organize those sessions here and there to bring together the different communities at the campus around all the technologies researched here at the campus. And thin films is definitely one of those. And yeah, having all the talks and conversations with the speakers before the event, you really feel, okay, this is really a community, also quite condensed here in the region. So it's nice to have you today talking about what you do in thin film tech and especially in clean tech applications. So I won't take too much of your time. Auke will start in a minute with a broad introduction about thin film technologies, explain also a bit about the landscape, and then we have three shorter presentations about applications in clean and sustainable energy applications. And afterwards, you have much more time to continue your conversations with the demos, which are built outside. So, welcome with me, Auke, for his introduction, and give him a big applause. Das kommt zum Klicker.
Yes, Auke Kronemeyer. I work here at TNO Holst Center here on the campus. And I say TNO Holst Center because first it was Holst Center that actually got established here in 2006. Philips asked when this was still a closed campus that you probably all are aware of, that they wanted to open up this campus to what it is now, this community of people that you are now. And so in 2006, they asked TNO and IMEC to set up, at that moment, an Open Innovation Research Institute. And so the setting that it actually got into, developed, was actually that in the building, people work for TNO and or IMEC, and Holst Center is actually a brand name. And within Holst Center, TNO is responsible for large area thin film technology. That's why I talk here today. But the setting is actually that we, as TNO, have been founding fathers of more of these brand names. So you will see that there's actually a TNO person talking here, but depending in which application domain we are active, we work under a different brand name. So we will have today also Sjoerd talking. Sjoerd is talking from the Soliance perspective. It's also TNO, but within Soliance you work with different partners, knowledge partners and also companies in a certain ecosystem to bring that technology to the market. That's the goal of TNO, and we have a number of these brand names we're currently working on, and they will come back in this presentation as well. So what's the added value? The added value of such a joint innovation center is really also working with and for companies. So doing it really together, having, for example, also what we call industrial residence. So really having people from these companies work in our R&D teams to actually sort of internalize the knowledge that we're building up. So it's very important that on this campus we try to do that whole ecosystem development. And where does it stem from? Just a short introduction, I'm not going too fast, but we all know we're here in the Eindhoven region. We all know Philips was instrumental in this whole ecosystem here. So of course Philips founded the NatLab. First director of the NatLab was Giel Holst. That's where the name HolCenter also comes from. I haven't been here for this whole long time, of course, but I hear Philips has been also instrumental in getting the knowledge build-up then also going. So taking the time and invest in the education. So TU Technical University actually got built here. And now we are at the stage that you build a world-class open value chain. So open means we here in the region, we connect with each other, we talk about our problems, our challenges together, and then come to a shared solution already in the R&D phase, in the development phase. And we are all aware, I would say, of what kind of companies have spun out of this region, of this site, and what they're doing now. But just to bring that a little bit in perspective, this is a slide. So I took the slides from Mark Hendricks, a boegbeeld of the TKI sector, high-tech systems and materials. So this is a little bit of a background. What kind of technologies have been actually stemming from this site? And it's pretty impressive, to be fair. It's very, very high-tech, very interesting things that actually happened here with, of course, the previous companies valorizing that massively on the ASML tools, on the Thermo Fisher, now or old Phi, then Thermo Fisher instruments. So it also creates a lot of business, it creates wealth, it creates jobs, maybe already too much jobs here nowadays in the region that we are, of course, now talking about the expansion of ASML and how is this region going to deal with it. Now, what's at the back there? This is a slide I took from the Next Gen High Tech program, one of the Growth Fund programs, and there they did an analysis about what are the markets that you can be active in. A couple of these markets will come back, but what are the key technologies that actually people are having experience in and that actually you bring into this market. And then you see thin film technology is one of the key enablers that we have in this region. And of course it happened to be what we're working on at HolCenter as well. At HolCenter we have two technology teams. One is for the additive technology, more of the printing, and one is of the subtractive technology that I do, that I will introduce to you in a moment. Because what is it? Thin film technology, we stack layers on top of each other. We pattern them subtractively with photolithography into functional layers, etc. You stack them on top of each other and they suddenly become a device. And here is an example. This is actually a thin film transistor. So the pixels that you actually have on your displays, I have displays here. The pixels, they have a number of transistors behind them to actually switch the colors that we see. And so if I draw here such a schematic with a couple of layers, which people will recognize as a thin film transistor if they know it. In real life, it looks kind of like this, and you have to imagine that this is the length scale we're talking about. So 5 millionth of a meter is this size. So that's what thin film technology is and can do for you. And you can do a number of deposition technologies, and you can do a number of patterning technologies. Some of you here in the audience will probably be quite familiar with, I would say, and otherwise we talk about it. So what's the differentiator in the market or in the market domain? You can do this in various production formats. So we all know that we have ASML around the corner, and actually there people work on wafer technology. And that works because you want to make very tiny chips, and you have a scaling down route that you want to make more and more chips on a single wafer. Well, that's a certain format. I won't talk about this too much. We know we have ASML, but what we do at HolCenter and a lot in the companies that we have here in the audience as well, is large area technology. So being able to deposit and pattern these layers over significantly large areas. And then you have two ways to manufacture that again. You can go for a batch-to-batch process, so plates, glass plates very often, that's how your display is being made. That can go up to this size. This is actually a real panel going through a display factory, 2.2 by 3 meters wide. And that's where you can scale through. And also you can do it roll to roll, like a paper, and then you make the meters by actually doing a lot of roll-to-roll processing, and then you get to the cost down of the product. Now, how does it look like? These are a couple of photos just about how does such a lab look like. These are labs we have here, of course, at the High Tech campus, and we are adapted to that. Also, part of these labs were previously Philips laboratories, and now HolCenter actually owns them, took them over. Now, what did we do with it, for example? A little bit of history, then to the future. So Philips, for those of you, that, of course, in the know, they worked a lot on OLED at that time, 2006. OLEDs actually die when you put them in normal air, so you need to encapsulate them, it's what it's called, a number of layers on top of them to actually keep the air out and the water out. Now, that's what we worked on. It was transferred to fabs. You start doing that in the laboratory here within glove boxes that, of course, are contained environments that there's no air. And at a certain moment when you've done the sheet-to-sheet, you want to scale up to roll-to-roll tools. So we demonstrated that you can do very good encapsulation based thin films on roll-to-roll layers. Moving that, and I make a connection with Sjoerd already. I'm not going to take away your thunder completely, but this is how Soliance also as part got started. So a lot of things were done for encapsulation on OLEDs, so you can do certain lifetime predictions. But then we also realized you can do also these encapsulations on, at that moment it was OPV, organic photovoltaics. I don't think the world is working so much on organics anymore, but perovskite photovoltaics, etc. You can do still a lot of encapsulation on solar cells, make flexible solar cells, and also build them roll to roll. Sjoerd will tell you all about that. Now, what we did also at Hulst Center for a while was stacking actually towards stacking these layers, 15 layers on top of each other to make flexible displays. So this, I also worked in flexible displays for eight years or something. So at that time, impossible to do. Nowadays, you buy your Samsung Fold phone at the Coolblue, where I was also in Den Bosch last weekend. So transfer technology, we are also aware that what we do in the fabs here in the Soliance building, we know that what we actually have as performance, it has one-to-one and 95% the same performance on the glass plates in a factory. So we know what we do here in our labs in Eindhoven, it transfers into these big factories, and that's a key enabler, of course, to start transferring new technology that we will work on also into these factories and to the market. So if you look at, 15 layers on top of each other, the transistor comes back again, and here, of course, you have a layer where you emit light, because it needs to be a display. If you change over slightly, now it's a slightly different image, but it's the same thing, a thin film transistor, and now something is on there that actually absorbs light. You can see that here, there is a low current, and when you shine light on it, there is a lot of current. Then you can make optical images out of it. So we worked a lot with Philips again on actually curved X-ray detectors. So a lot of things we were still doing were on foil. Here you curve around the bone and you can do nice CT scans of a bone with optical imaging. A couple of other examples here, fingerprint scanning based on optical images. And with a couple of other companies we demonstrate. Also here you can do vein detection. So a lot of things that can now be done on detection of light. Now, also, if you can just remove the whole layer and do the capacitive test, the fingerprint scanning capacitively, that's why we have today Touch Biometrics also exhibiting here. So they recently actually showed that they can do their product, which is here imaged nicely, which is based on capacitive fingerprint scanning. So same technology of displays moving into a different new application domain. Now to the future. These were all examples of what we already did in the past. Now to the future. So we move away from flexible displays and imagers. We want to move them more onto the skin, etc., to do measurements on the body. But for today, I want to also talk about 3 different application domains that we work on now. For new markets, energy, we work in health, and we work in chip packaging. So what can you do there? Now, energy, I don't think I have to introduce why it's so important, but there's 2 modalities. Of course, you can store electrochemically into batteries. You can also store in molecules, and for example, one of the candidates is hydrogen. Now, what do we do in this domain? I think today, is Lionfold today here exhibiting? Are you? Yeah, very good, yeah. So Lionfold, also startup of TNO Hulst Center, developing here on the campus 3D solid-state batteries. So this is an example. This is kind of like this is a battery. You don't see it, of course, but this is a battery with thin films. It consists of anode, it consists of cathode. And you do this over a scaffold, making a lot of surface area per volume, optimizing capacity of the battery. So now startup being very active and getting a lot of funds. So still helping them out to scale through with their technology. Another example, I think we have 3 ALD, and Sander just walks in. We have 3 ALD companies here in the Netherlands, Spark Nano, Salt, Galpana, all 3 here, where we try to look into the battery domain, how we can position their technology, spatial atomic layer deposition, to actually enhance the performance of batteries. So what can spatial ALD do? For those people that know normal ALD, ALD can do very conformal and very high quality layers. Spatial ALD can also do that, but at high throughput. And you need the throughput for the battery production. And so what an example is that we work on together with these companies to demonstrate the technology in batteries is here also with the German Institute, ZSW. We demonstrate that on a battery cathode, or an anode for that matter, but this is an example with a cathode, if you can coat over that material a very thin layer of these important materials, that you can do surface enhancement, etc., you can demonstrate that you can have the lifetime of the battery significantly improved. And this measurement is still ongoing, but what you need to see here is that normally the capacity of your battery starts fading if you start cycling. And that's the black curve. And now when you put this little, 2 nanometer layer probably or something, I don't know where it says here, but you put a very, very thin layer of aluminium oxide in, and you can actually make sure that the cycling stability is going to improve significantly. And of course, this is how we want to position the ALD companies into this market. Going back to the example that we did pre-CVD for the OLED stack, think about it, these are the same images that I just used. You see that these two tools now, this is the next version of that tool. And so what happened during the couple of years is that actually Leiden Jar, Leiden Jar started, and they actually want to use PECVD to actually grow silicon anode material. So silicon anode gives you around 40 to 70% enhanced capacity in batteries. So we're also heavily working with them to position them with the ALD companies potentially again, and working with solid state electrolyte to make new next generation batteries, to make the difference there with our technology here from the campus. So we do that by building also ecosystems. So again, it's very important that you don't do this all on yourself, but you build ecosystems. How do you want to go with the different competences that you have as different companies to the outside world internationally, and how do you position yourself? Now we do that within batteries, within something called Battery Competence Cluster NL, and we have a lot of technology development already ongoing with NextGen High-Tech, another Groeifonds proposal coming. And we have a longer term idea that we can do this in hydrogen as well, because from far away, batteries, or at least for me as a sort of non-technical person nowadays, batteries and electrolysis look very similar because they need surface area per volume. So that's what we try to achieve here as well. The first steps we're making again with our ALD companies. So actually we decrease the use of iridium. Iridium is used as the catalyst in hydrogen production. So at the surface, you need minimum amount of iridium to actually do a right proper conversion of water into protons. But because if we now have the plans for 2030 for all the hydrogen that we want to install, we need 250% of the amount of iridium that is yearly produced. So if we can significantly reduce that use, we are doing our best for the climate change. Now that's one step that we have been demonstrating again with ALD roll to roll, but we have a longer term roadmap also where we can do more of these intricate stacking of layers like we do with displays, but now for integrated hydrogen electrolysis. Now I want to make a small step towards health. So it was not easy to make this step in my head, but hey, I just make it with you. So if you go from electronics to health, there is a couple of laws that you might be familiar with, or at least in electronics, we have Moore's law. So Moore's law says on this wafer technology with chips, you actually increase the number of chips in 2 years, or you doubled it in 2 years, and the cost of a chip goes down. The funny thing is for new drugs, so for if you're ill, for new drugs, there is a reverse law. So that's kind of annoying, right? So that means if I need a new drug to come to the market, it is increasingly costing more and more money to get that to the market because of the development cost, and because when these things, they are being tested, like they are tested on animals, etc., they increasingly fail. So what's the answer to that? So the answer to that is start actually with thin film technology to create environments, so also including now microfluidics, where these environment cells are actually human cells are feeling like they are in your and my body. And that means if they are really feeling like that, and I can give them nutrients and I can take the metabolites away, the afvalstoffen, what is it in English? The waste products. Then these cells, they feel like they are you and my body, and I can do tests on them which are way more representative for drug development. And that means also that we're bridging here two pathways. So you see again, we are making on panel level again microfluidics. We are reusing our knowledge in electronics, because also be aware, nerve cells and brain cells, they communicate with voltage pulses. So we can measure that again with electrodes. Yeah, we're bridging here that there's a scalable technology available to make products and to do it cost effectively. But nobody has ever tested whether these materials used in the factories are actually biocompatible. And the other way around, what we're bridging is people that do a lot of these things currently from the biology, from the cell biology side. They have demonstrated that you can do these cool tests and that you are more representative with the statements you can make on the tests, but they have never thought about how to scale up the manufacturing. So that's where bridging with this program, and this way we tend to think that you need to work in this multi-well plate format. It's a standard that has been set. If I look at the NOS journal, you see a cell biological lab of a pharmaceutical company, it's optimized in this format with automated pipetting. So we think you need to do this organ on chip, is what it's called, into this format. Now there's a roadmap there also that's first trying to do microfluidics and electronics, and at a certain moment try to implement more and more organs. And also within HolCenter with IMEC, we're also going to look at how does sensors, because I don't need to make with the thin film, with the large area thin film technology, every component. So we also know that chip technology on wafers can actually make very, very nice sensors again. Yeah, pH sensors or ion selective sensors. So what we're trying to do with IMEC within HolCenter is also that we're going to integrate sensors based on CMOS technology into the panel level technology. Yeah? And it's not completely new, because you have to envision that the television you have at home, at the side of the television, there's also chips placed to actually drive the signals into the panel. So we're just going to do this in a new application domain with new sensors. And this brings me to my last topic that I wanted to introduce today. So if I can put a sensor into a microfluidic environment, you can also see this into a normal way of chip packaging. So we see that packages where CMOS chips are actually integrated into the bigger system, and the fan out is being done to the outside world. Those packages are becoming more intricate over time. So people want to, for example, integrate the antenna into the package for 6G. People want to do high power systems. So the package is becoming more complicated, and, for example, with this antenna integration, also bigger in size. And bigger in size, again, brings me back to the fact that if you have a large area product, you need to have large area technology, and that's why it comes into the ballpark that we want to work on it again. Now there we have the first building blocks that we're working on. What are we learning here? So we are learning how to deal with significantly thicker films. So if we talk to the PCB makers, they easily talk on tens of microns thick films, and we generally come from a couple of microns. But still, they want to have a very high resolution, lateral resolution. So we're optimizing here the aspect ratio of the technology, and we're using lithography on panel size to keep the resolution, but we're growing our technology into the thickness domain for interesting packages. And here we have a couple of examples. And the final thing is then, if you can package actually just electronic chips, we also here, of course, here at the campus, we have smart photonics. We have a push here in the region to go to photonics. Yeah? So if you think you can package an electronic chip, there's a lot of interaction and a lot of sort of reuse of building blocks and technology processes that you're not going to package an electronic chip. You're also going to package the photonic chip, for example, of smart photonics here on the campus. And then also there we foresee that there's the silicon nitride platform in Twente, and at IMEC there is indium phosphide, which is happening here at SMART. If you can combine them, you can combine the best of both worlds. So there's quite some opportunities. That's where I want to end for today, where if we come with a history of thin film technology here in the region, with a lot of companies being active in historic, interesting fields, there is also ample opportunities in the future to go to new application domains. And I hope you all, including with me, are going to be successful making business of this. Thank you very much.
Thank you, Auke. So now with this talk, we have 5 minutes for Q&A. And Malou will help me with the catch box. Are there already any questions? If not, also all good. We also have later time at the networking.
Okay, does it work? Yeah. Short question on the iridium, on those electrocatalysts. There was a choice but it is known that iridium is far less available as a resource on Mother Earth than even the rare earth metals. So, obvious question, what other alternatives are being taken into account by Holcenter and its partners, like cobalt phosphate or what have you?
Very, very good question. To be fair, you shouldn't ask this question in detail now to me about what are the other catalysts. I know we're working on non-precious metal catalysts. I think why we started with iridium is, one, it's the baseline currently for a lot of PEM electrolyzers. And we, of course, are a bit, how do you call it? We want to help this ecosystem we have here in the campus. So we are a bit pre-depositioned, is that the English word, towards ALD. So we wanted to first show that ALD has merit in this domain by showing that we can decrease iridium use. But of course, there's way more, let's say, technology development that can be done to also first get maybe off the iridium or to other materials. Yeah.
Any more questions? Top. Then I think we save them for the break and continue with the talks. We thought we focused the application talks on the clean tech field. So really on sustainable energy applications. And Sjoerd will begin with introducing the solar panels, which you also see one building further at High Tech Campus 5, building High Tech Campus 5. And you will explain a bit more about the technology behind and the solar applications from TNO.
Okay.
Thank you.
Thank you, Marina. Okay, so nice that you're all here. I would like to give a presentation about creative thin film solar. So let's have a look. This is basically the solar ivy that you may have seen here on the campus. Basically, you see here a nice photovoltaic facade, basically, and it has a rather different shape. And I would like to discuss, let's say, how we get there by start working on thin films. Before I do that, I think it makes sense to kind of give a bit of introduction about what is important for these solar energy in the Netherlands, as an example of the fast development in Europe and global. So I think it starts with the Paris Agreement. There we say, okay, we need to reduce the carbon emissions. And then in the Netherlands, this was followed by the Klimaatakkoord, as we call it. And in the Klimaatakkoord, it tells us that in the Netherlands, we need to increase the share of solar. And so we go from 10% to 20% to 33% in 2050. Now, this also means that we not only increase the share, but also the use of electricity. So this is called electrification. So this means that if we make a plot of the needed PV capacity in the Netherlands versus time, versus years here, then depending on the scenario, we need to grow fast or very, very fast. Now, if we do that, we also need more area. So we need to place these solar panels somewhere. So it means in 2022, I think we had about 18 square kilometer. In 2030, we need 200 square kilometer. And in 2050, we need 1,250 square kilometers in a small country. So the question is, where do we place this? This has been investigated or studied in great detail, and again, several scenarios come out. And you can place it on rooftops, you can place it on utility buildings, infrastructure, you can put it in the landscape or on water. And then you can see if you, for example, go for 80% of the rooftops that are where you can actually mount PV on top, and 80% of the roofs of utility scale, then you get already very far for the targets for 2050. So it's actually possible to mostly use area that's already in use and just give it an additional function. There's also other ways of doing it. You can have perhaps more on infra or on land. You can also think about water, inland water, or even water with higher waves. You can find solutions there. So basically what we then distill from this is that what we need is probably integration, so that you actually can utilize as much as the rooftops as possible. And maybe not only the rooftops, but also the facades, as the example given earlier. And the same is for utility buildings. Very often, these very large area roofs, they require lightweight solutions, and the standard solution is not really applicable there. So you can work on that technology. Also very important is to come up with higher efficiency. So for that we develop technology where you can stack 2 solar cells on top of each other and increase the output by a factor of 1.3. This huge increase in the application of PV also is a great opportunity for business, I think. And so in the Netherlands in the next year there will be an annual turnover in solar for these panels only of about 1 to 3 billion a year. In Europe this will be more than 10 times, and on a global scale it will be maybe 100 times. So this is a huge opportunity. And this is also what the EU sees. It's an opportunity, but they also say that this is of strategic importance. So they want to have this technology in Europe. And we are happy to help there. Okay, so thin film in PV. So where do you find it? Well, this is a silicon solar cell. It's 95% of the solar market, at least. And if you look at it, it is a wafer that's maybe rather thick, but all the other layers are thin. And we use methods like screen printing, sputter, CVD, and PVD to make such a solar cell. This is the work that TNO is doing with partners mostly in the north, in Petten. And here we work mostly on thin film technologies like CIGS and perovskite and other technologies. And there again, it's basically all thin film. So now, let's say the thick film here is now replaced by a solder coated layer that is less than a micron typically. And here we use again PVD, sputter, but also slot die and spatial ALD. Here is again possibility of using ALD and sputter processes. So this is how we can make the new type of solar cells, and we can actually also combine a crystalline silicon with a perovskite to make tandems. If you go to thin films, you can also make it flexible, and then you can go to roll, as I will show. Okay, so perovskite solar cells, you can have an axis, let's say a mechanical axis and an optical axis here. And you can make devices that are, for example, rigid. They are on this side, they are on glass, so you use sheet-to-sheet processing. But you can also make them flexible, and then you can go towards roll-to-roll processing. You can transmit light, so here we call it this translucent part of the light is transmitted, but it's the full spectrum. And you can also allow only a part of the spectrum to be transmitted. And you can also, of course, have a reflective background to even reflect back the light that was originally almost transmitted and reflected back into the solar cell to crank out the last amount of current. As I mentioned, you can make a combination of perovskite and crystalline silicon to make a tandem device, and then the top cell, let's say here the perovskite, absorbs more or less the blue part of the solar spectrum and transmits the infrared part of the solar spectrum. So in this way you can achieve an efficiency that's 1.3%, a factor of 1.3 higher. And that is also what we see now in the lab. If we look at what's published in literature and what we measure in the lab, we see that there is a strong increase in efficiency over time for this type of combination. But actually what you can also do is you can also make combinations of perovskite with perovskite. And that is this trend here, and now reaches about 29 to 30%. So what's maybe interesting for the community here is that we have let's say, a wide range of tools that can actually be used to make thin layers. So we have sputtering, slot die coating, PVD, spatial ALD, and laser scribing. So these are all techniques to apply layers, and this is a technique where you can actually make patterns, or you can scribe it. So this is all sheet to sheet, so you go increase the area, you use scalable techniques that are industry compatible, and you go to larger area. In a similar way, we can work with roll-to-roll technologies to make flexible devices, and then have a higher throughput, go with flexible or curved applications, and work towards PV or solar cells as an added function to a certain application, not as an application by itself. So we're working in this area, and we expect actually to increase our tool set here. So this is maybe also opportunities for companies here. This is maybe a nice example. I hope that I can show. I don't have a lot of time, but this is an example of a roll-to-roll process where you see here a coating entering the device, the slot die coater. Here we apply a wet layer. It goes into the oven on a metal foil from Hyatt. And then when it comes back from the oven, it's cured, and you see that the wet layer is now converted in a perovskite layer, and this can be rolled. So as I mentioned, this is, let's say, a carrier of Hyatt Solar, one of our partners, and also present here today. So you can have a talk with them about this new technology that they are developing together with us. Actually, you see a very nice edge here, very sharp. And this is now the absorber layer of a new perovskite solar cell that can be made roll-to-roll. Now we have a flexible solar cell. Now we need to integrate it in an application. And you can have very nice examples, but very often it's really handcraft to make it. And therefore, it's hard to get to volume. So what we wanted to do is work with robots and see if we can automate the manufacturing process. For that, we came up with an idea of having roll-to-roll processing of flexible solar cells, then what we call mass customization of a module, but not a finished module, a module that you can later laminate on any type of building element, for instance, for housing or for infrastructure, for cars. You can think of a wide range of applications. So this is basically how we move now forward. And this is the line that I just showed. I have another movie, don't have time to show it, but I can show that the rolls that come actually out of this machine. What we do is we put all the components of this semi-fabricate in this line, and then build this type of foil with all the functionalities. And with that, we go to applications like this, where you see these solar panels integrated in this solar ivy. And this is together with Mia Soleil and Flexipol. So we come up with new ideas of how you can bring solar to a facade and use more of the solar energy that is available, but just needs to be harvested. Okay, we do this with many partners on production, equipment suppliers, materials suppliers, process control. We also work, of course, with many funding agencies and our knowledge partners, Solar Lab and Soliance, indicated here. These are the startups that came from this work, and these are the take-home messages. Basically, I explained that there is a link from the Paris Agreement all the way to making integrated and more efficient solar cells, and this also could bring back solar industry in Europe. Explained a little bit thin film in solar devices, explained the processing tools that we have, and our vision towards integrated solar. And with that, I would like to close, and I would like to thank the team, or part of the team, where we really collaborate continuously. And if you have any questions, I'm available after this presentation. Thank you.
Thank you. Perfect. We continue smoothly now from solar to carbon capture, and Mark is coming down first. So the stage is yours.
Thank you.
Give him a big applause.
I would almost say now for something completely different. I have a short presentation for you, and will be available here after the meeting for some questions if you want. This presentation is merely meant to inspire you and also stimulate you to also think of very different applications of thin film technology. And at Carbion, we have found one. My name is Marco, operations at Carbion. And to get you inspired, I will start with after this slide, with a short movie, and hopefully it will run smoothly. First time right.
A long, long time ago, organic remains were safely stored deep within our planet, where it turned into carbon compound. Let's fast forward to the Industrial Revolution, when we first discovered that we could use this carbon to fuel our societies. But there's a catch. Every carbon particle we burn turns into a CO2 molecule that is filling up the atmosphere, which is bad news for our planet and for us.
Bad news.
What if we could reverse time, clean the atmosphere, and use this CO2 for something good? Carbion's technology can do just that. Capture carbon dioxide from the sky. No time machines needed. Our carbon-soaking sorbent cleans the air and enables us to store or reuse the CO2 in fields such as transport, agriculture, and construction. Let's power a sustainable economy while restoring our planet. We are Carbion, and we capture the sky.
That's a nice teaser, I think. I'll explain to you in a minute. I see a relative there. Hey, Ton, that's a long time ago. Explain to you in a minute what this thin film technology actually means for us and how we get this to work and why it's so special. But this presentation was called carbon removal, and I think it's good to explain firstly what that is all about. And that's something that a lot of people actually still, I would say, do not know, and it's about this. Because we have been emitting, or actually burning fossil fuels for, let's say, 200 years now, in a very high pace. And you can actually compare it, the CO2 emissions that it created, as a sort of blanket that we put on top of our planet into the atmosphere. And this is this blanket. And we have put more and more, ever more blankets onto our planet. Why? That's causing global warming. And now people say that, okay, we have to get to zero emissions, but basically zero emissions means that we do not put any more blankets on top of our planet. So we do not emit any more CO2, which is a major challenge as such. But that will not help us to get rid of global warming. It will actually linger on for at least 200 to 300 years, as the models predict. So but what we actually should do is remove blankets. And getting back to the metaphor, we actually have to remove CO2 from the atmosphere. We have to draw it down from the atmosphere. And that's called carbon removal. That's removing emissions. And one of the ways to do that is a technology solution that's called direct air capture, and that's exactly what we are developing. And direct air capture means to capture CO2 directly out of ambient air. And then, of course, you have to store it away in some way. It already exists. It's being developed by now for almost 10 years. But there are several challenges, and one of them is that it's way too expensive. At the moment, it costs around 500 to 1,000 euros to capture 1 ton of CO2. That should go down to 100 at max. And that's quite a long way to go still. And also, it needs to be scaled up massively to have at least an impact on climate change. So we're not talking about tons of CO2, we're not talking about thousands of tons, not millions, billions. It's called gigatons. It doesn't have to happen overnight. If it could, it would be nice. But that's a target to reach by mid-century, that we are able worldwide to capture at least 1 gigaton of CO2. And from there on, scale it further. Now, why is it so expensive? And you can see it in this picture, because this is what it looks like right now. It's massive machines, very huge and expensive equipment. And as you can probably also see, this is probably not the best way to scale it up. And that's actually where our technology comes in. And I'll explain in a minute how the thin film works on that. But this is what we do. We make machines much smaller and easier to scale up. And we can reach a capex below $50 or euros per ton. And that's exactly where the thin film comes in. Because how this works is direct air capture works with a material. It's called a sorbent that actually binds CO2. So if you blow air through it, the CO2 binds, and when you add energy to it, the CO2 gets released again, and you can cycle over and over again. And in most materials that are used, they also use porous materials, but the clogs or the pores are actually filled with sorbent material. And that makes this process rather slow. And we have managed, and this idea was born at TNO Soliance here, so that's the link to the previous presenter. We managed to use this material, actually it's a carbon fiber material that we are testing, to functionalize it through the entire surface area, large surface area, without clogging the pores. And that means that we have a huge surface area where we blow air over, and all the area is used to actually capture CO2. So instead of having a very slow process, we have a fast process. We call it a fast swing process. It's the swing process of absorbing CO2 and releasing it again. And that means that we can capture much more CO2, roughly 10 times more, in the same period of time as existing methods. It also means that our machines can be much simpler and much smaller per amount of capacity that we want to capture. And there's another advantage to this fast swing method. It's a bit technical, but it also means that we can keep the energy consumption down, which also contributes to lowering the costs. So there are various examples and advantages of using this thin film material for carbon removal. Now, these kind of machines, of course, this is the basis material, the thin film. We have to make a machine around it. I will not go through all the steps, but basically what I said, it means you need to have a machine that sucks in ambient air. It blows through the sorbent material, through the thin film. The CO2 is captured. You apply some energy to it, and the CO2 is released again, and you have to store it away, or you can reuse the carbon compound of the CO2. And then the process can repeat and repeat and repeat. And our idea was picked up by the XPRIZE, actually this guy, Elon Musk. He's doing some other things these days, but if he's good at anything, I think it's in recognizing promising ideas that can really scale big. So that was recognized in 2022 when we won the XPRIZE. We're one of the finalists of the XPRIZE. We won $1 million in prize money, which is a lot for a startup, I must say. And from there on, we started building our lab equipment. So we are now in the phase, actually, that we came out of our lab testing. This is the test setup that we use here in Building 29 at the ITEC campus to test our thin film samples. We have scaled that up to a first indoor prototype. We call it WALL-E. Yeah, we all have Disney names for our machines. We actually have 2 of them. Of course, for a startup, these are really big investments, but this is really our test working horse, so to speak, to test on a larger scale, and the larger scale is depicted here in this nice color pink. It's actually a reactor that is filled with thin film material. So we suck in air from outside, and this reactor actually captures all the CO2, and then we can vent it out again. Unfortunately, we have to vent it out now because we don't have an application for it yet. But that will change over time. The next step is, this is actually Hans. Hans worked at TNO when he came up with this idea, working on thin films for solar panel applications. And yeah, we had our first proof of principle already in 2022. And it took us, as you can calculate, a few years to get this fast swing principle working on the thin film materials. But that's the time it took to actually create our recipe to make the thin film. The X Prize was a major breakthrough for us and our team to grow in terms of investments in prototype materials, but also to grow our team. And the first reactor, the one in pink, is now shown in green. And lately we also had a breakthrough, a press release around a breakthrough that we can also keep our energy budget low enough, which is very important to further scale up. The next plans are, we are currently finalizing our Series E would be a bit far, funding round, and that will bring us to the next level in the sense that we will build our outdoor machines that we will have ready here for verification and validation purposes at the HiTech campus, but we will also ship them to our first pilot customers on different places on the globe. And from there on, our plan is to scale up, and we have to scale up really rapidly to make this work. And the machines might look like this. This is an artist's impression. They probably will not look like this, but already from the previous presentation, I'm sure that one of the next ideas will be to wrap it in flexible solar panels. So we also directly have the energy intake there. So that might even be another application of thin films. But anyway, I would, this presentation was meant to inspire you that there's a lot of possibly also applications of thin film technology that we haven't even thought of, but started here at the HiTech campus at TNO Soliance with a crazy idea. We are now in the phase that we might have, and of course we think we have, an application that can actually help to solve one of the biggest challenges of our time. Thank you very much.
Many thanks. Thank you, Marco. And now we will hear from Diederik about batteries, and especially how thin film and spatial ALD can help to even make them better performing. The stage is yours.
I'm Diederik Spee from Colpana Systems, and today Colpana Systems is an equipment manufacturing making spatial ALD roll-to-roll machines, and today I focus mainly on the battery application and how we think we can use that to make batteries better. So here's the summary about Colpana Systems. We are a very young company, founded in 2021, based in Delft. We really focus on high volume roll-to-roll systems. We are not the only company actually present focusing on spatial ALD equipment. So we also have Spark Nano, I think, and Salt with a demo after the talks. And I actually see more people in the crowd that maybe even know more about spatial ALD than we do. But we really focus on this is the wrong one. On the high volume roll-to-roll systems. And the markets that we focus on are flexible displays, flexible PV, as Sjoerd showed us, and batteries, which I will focus on today. And since we are a very young and also small company still, we do not really have a large research. Actually, our research department is here. It's one person. So that's why for us it's extremely important to actually collaborate and co-develop stuff with other companies. Hyatt also present here, Cienza, institutes and the battery competence cluster, for instance. Now over to the batteries. Usually when you, this doesn't fit. Usually when you speak about optimizing batteries or characterizing batteries, you speak about the bulk properties of all the components in a battery. So you would think about how much lithium ions can I fit into a cathode or an anode, what is the conductivity of the electrolyte liquid, stuff like that. Might be even economical, what does it cost, this material or the anode material. But when you really look into detail on how a battery looks like, there's actually a lot of surface involved. So the electrodes are usually porous. The electrolyte is going all the way into the electrode. And this interface is determined for a large part the performance of the battery. So when you start charging and discharging a battery, usually the organic electrolyte will react chemically with the electrodes, and you will form a solid electrolyte interface. And this interface can actually have, of course, many properties. So it can be insulating, it can be ion conductive. So that is one thing that determines that the properties of this surface determine the actual performance of the battery. And another thing is that when you start forming this interface, you use up a bit of the electrolyte and a bit of the electrode material. So actually the capacity even goes down when you start using the battery, just because of this. So if you can manipulate that interface with a thin film coating, make it more stable, or even completely avoid the formation step. So and in formation step, I mean growing this solid electrolyte interface. You can actually make batteries more stable, give them a longer lifetime, and also make them cheaper. For instance, because this formation step is usually done in a very controlled way. So when a battery is finished in a battery line, you discharge and charge it a few times, very slowly, very controlled, to actually give the solid electrolyte interface the right properties. And this formation step can, for some battery concepts, even make up like 30% of the cost of a battery. And looking at novel battery concepts, so maybe you want to use pure lithium metal anode, there's also a good function for a thin film application, because lithium is very reactive with air and water, so you might want to add a buffer layer to that. Or going into high aspect ratio battery concept, this of course looks very much like what LionVolt does. Apparently LionVolt is also present, I don't know, but and there deliberately you increase the surface area in your battery, which makes it even more important to make this thin film of interface, to give it the right characteristics. Now, why should you use spatial ALD for that? Many of you probably know ALD, and it is a self-limiting reaction. So what is the consequence of that is that the coating is extremely conformal. And this is what you need when you look at this picture, because actually it's important to make this layer thin, homogeneous, but also homogeneous all the way up, all the way down actually to the current collector. So this is why ALD is the thin film technology to choose if you want to coat a structure like this. If you would use, say, PECVD, a more directional form of thin film deposition, you would probably coat the top of the electrode but not the inside. Now, if you want to go to high speeds with ALD, you can not separate the ALD steps in time. You can separate them in space, and you have spatial ALD, and you would end up with a deposition head, something like this. And you can do ALD faster, but you end up with a few new challenges. One of them is, of course, keeping the gases separated. They're all present at the same time, and it's very challenging to keep them separated. For that, you put nitrogen knives, for instance, in between exhausts. And it's very important to keep this gap very small, so to control your substrate and your deposition head very well. And another thing is that If you want to make a significant layer thickness, you need a very long deposition head actually. This 4 things is what you need to do one ALD step, one ALD cycle. If you want to do a lot, you end up with a very long deposition head. Unless you go to flexible substrates, with battery electrodes of course are also. Then you can use a round deposition head, and when you start spinning that, from viewing from the substrate, it actually becomes endlessly long. So you circumvent that challenge. But having a flexible substrate, it becomes difficult to control this gap very well. And at Kalpana, we think we solved this issue by doing a few things. So this is actually what we do. So we have a web transport mechanism in which we transport our substrate in a helical manner, very controlled. And in this way, we first of all don't have the web entry and exit inside the process, so we can have it very stable. And on the other hand, we can have a very highly accurate substrate positioning. And then focusing specifically on batteries, it is also important to note that the position of the battery electrode in this case is so well defined that it's independent of our process pressures, which might come in handy when you actually see that it's a challenge to supply and remove the excess gas from the porous material. You want to supply it with a high pressure and actually take it out with at least in the exhaust a very low pressure. And this is the only way we think you can actually coat fast a battery electrode. And you need to go fast because actually when you look at high volume battery production, you see that you usually should go up to 50 or 60 meters per minute of web speed. And this is what you really need to end up in a gigafactory. And we think we can reach that, so say coat 100 square meters with a few nanometers of coating, at least with the larger one of the 2 pieces of equipment that we're developing. Yeah, that's mainly all I had to say. This is actually a summary. So manipulating the interfaces of batteries can improve their performance significantly and even reduce the cost of batteries. ALD is the most suited method to do that. And we think for coating porous materials, you need something like we're doing, which is not basically an ALD invention. We didn't invent ALD, but we did invent a new way of web transport, which is very well combined with ALD to make it compatible with mass production of batteries. Thanks.
Thank you all for your presentations and your insights. So after 1 hour of a lot of input, we now have 1 hour, if you want to stay that long, for some demos. So or some demos were already mentioned. So Hyatt will be there also with solar panels 10.0. You also brought some samples of the solar panels at HTC 5. And then we have Touch Biometrics with a not clean tech, but another application, a fingerprint, biggest fingerprint sensor. Sorry. And then we have Spark Nano, Eurofins, and Salt also represented with a demo. So take your time, walk around. We also have some drinks for you. So thank you for joining and see you next time. Bye.